water. So this is my, that's the title is like this. And so I want to talk about first Floer theory in simple geometry, how it is good. And then secondly, I just present you some preliminaries, and then finally I want to talk about our work. So yeah, actually we have several kinds of Floer cohomology theory, and one is for periodic Hamilton systems, which you already heard from Yong-Yong's talk. And it can be used to show the existence of periodic orbits of periodic Hamilton systems. And also, you can cook up some invariant of Hamilton diffeomorphism, that is spectral invariant. And then the Entroph and Podolevich use this to obtain very important quasi-quasi-morphisms and partial symmetric quasi-states, and then got some applications. So here's wider Floer cohomology theory. Sorry, this is not yet. So then, not only Hamilton diffeomorphisms, we can also define Floer cohomology for simplex morphisms. And then, actually, we can use it to show some C1 closeness of Hamilton diffeomorphism group in the identity component of simple morphism group, that is so-called flux conjecture. And there's also some nice computations of Floer cohomology for surface diffeomorphisms. And so here is the Floer cohomology theory for wider setup, that is for Lagrangian intersections. So one can use this technology to show persistence of intersection points under Hamilton deformations, which I may mention later. And also, if the Lagrangian submanifold is displaced by some Hamilton diffeomorphism, then somehow we can get how big the Hamiltonian diffeomorphism should be. And also, this Floer cohomology for the Lagrangian intersection is very important in the study of square category, because they actually play a role of morphisms in that category, and which is really one of the important ingredients in homological media symmetry context. Okay, and then there are more variants of Floer cohomology theory in simple geometry. And because I'm in Korea, I just want to mention these two things which are very much studied in Korea. Namely, the Felder actually studied moment Floer cohomology and also Rabinowitz Floer cohomology. Okay, so there are several things, and they are very useful. So I just start simplistic preliminaries. So probably it is not necessary to say this, but I just want to fix some notations. So M omega denotes a simplex manifold, namely manifold equipped with a closed non-zero 2 form, omega. Then any such simplex manifold is locally diffeomorphic to kind of standard R to N equipped with this omega 0 form. This is known as Darboux theorem. And typical examples of simplex manifolds, I may list up only two here. So one is cotangent bundle manifold. So X is a manifold, and then you consider cotangent bundle. And then you consider certain canonical one form, which is already you saw in the first lecture. So this is written as a sum of Pi dQi, and Qi local coordinates on the base manifold X, and Pi as a fiber coordinate. And then you take an exterior derivative, it is certainly closed form, and you can see that this is actually locally isomorphic to omega 0, so therefore it's a symplectic form. And another class of manifold examples come from Kähler manifolds. So if you have a Kähler manifold, forget about complex structure, just keep Kähler form, and then you get symplectic manifold. And if you have a simplex manifold, then you can always find some nice almost complex structure compatible with symplectic structure. So here I gave two conditions. One is so-called compatibility condition, another is tame condition. So anyway, you have such a almost complex structure, and also these complex structure form a contractive space. So okay. Now the second thing I want to remind you is Hamilton vector field. This is also you found in the first lecture. So if we have a function on the manifold M, then you can take its exterior derivative, and then because then the omega is non-degenerate, so therefore omega gives you one-to-one correspondence between vector fields and one form. So this closed one from D, exact one from D8 corresponds to a certain vector field on the manifold, that is so-called Hamilton vector field associated to this function 8. I denote by x sub 8. And in this local, if you consider the case of functions on even dimension vector space, and then the Hamilton vector field with respect to the omega 0 is just written in this form. And Hamilton vector field actually preserves omega. It's an easy consequence. So it gives you symmetry of the symplectic manifold. So if you have one function, you have Hamilton vector field. But you have a family of functions. Actually, this is not correct. This is just opposite. But if you have a family of functions, then you have a family of Hamilton vector field, and then you can integrate it to get an isotopy starting from identity. And then you can see that these isotopy preserved symplectic form. We call such a diffeomorphism Hamilton diffeomorphism. Namely, a diffeomorphism psi is called a Hamilton diffeomorphism if psi can be written as a time 1 map of certain Hamiltonian capital H. And I will denote by Ham of M omega the group of Hamilton diffeomorphisms. And this is. So the next thing I want to remind is Lagrangian submanifold, which already you heard. So submanifold L is called Lagrangian submanifold if it enjoys two properties. One is just the restriction of omega just vanish, and secondly, the dimension is just half of the ambient space. Then such a thing appears in many interesting situations, and as Yonggen-Oh mentioned, everything is a Lagrangian manifold as Alan Weinstein put. So here are just easy 3 examples. So as I told you, the cotangent bundle is an example symplectic manifold. And if you consider closed one form on the manifold, and then you can take its graph. I mean, you can think of closed one form as a cross section of the cotangent bundle, and then it gives you Lagrangian submanifold. And if you have a symplectic morphism, then you consider its graph. Then it gives you a Lagrangian submanifold in the product of 2 copies of x equipped with symplectic form minus omega plus omega. The third one is the following. So if you consider circle in R2, and then this is Lagrangian, and then if you take n copies of them and then take product, you have a Lagrangian submanifold. And this example can be extended to the so-called Lagrangian torus fibers in toric manifold. So in toric manifold. So maybe this is a very easy case of that. So this is Lagrangian submanifold, and Lagrangian submanifold has some interesting property. So I just want to mention one thing here. So they are reluctant to be displaced from itself by Hamilton deformations. What does it mean? So there is one sample theorem. This is due to Rodenbach-Sikroff and Hoho, maybe in 80s. So let's consider the 0 section of the cotangent bundle, and then consider any Hamilton diffeomorphism. on the cotangent bundle, then the image of the zero section must intersect with the zero section. So you cannot really displace it. So therefore, yeah, you cannot displace it. In general, you can displace. You may displace. Like I have a small circle, just a circle in the R2. Certainly you consider big translation. And then translation is Hamiltonian diffeomorphism. So therefore, yeah, you can displace it. But you need some amount of, some big Hamilton diffeomorphism. So how to measure the size of Hamilton diffeomorphism? That is actually done by the Hofer norm of Hamilton diffeomorphism. So I don't want to remind you this. But so here I just mentioned Tekhanov's theorem. So if you have a closed-embedded Lagrangian manifold inside a nice simplex manifold M omega, yeah, geometrically bounded, maybe you can just forget and then replace it by a closed simplex manifold, or maybe just R to N. Then there is a constant depending on the submanifold L. This is positive constant, so that the Hofer's norm of Hamilton diffeomorphism, which displays L from itself, is at least this number. So you need some amount of energy to displace it. So this is Tekhanov's theorem. Okay. Okay. So this one I can skip because you already heard of it. And this also you heard of it. So now I want to explain a bit about Floer theory for Lagrangian manifold. So here is just a naive idea. Let L0 and L1 be pair of Lagrangian manifold, and consider the space of paths starting from L0 and end up with L1. And then on this space, we can formally define one form, alpha. So let Xi be a tangent vector on the path space P. Then we have to assign this Xi some real number. So it is given by this. So Xi is a tangent vector of the path space at gamma. That means you have a vector field along gamma, right? So you have a vector field of manifold M only defined on with the tangent vector at endpoints tangent to L0 and L1 respectively. Then you define alpha Xi by this formula. So Xi t and gamma dot t. Gamma dot t is a t derivative of this path velocity vector field. And then we can show that this is actually kind of closed one form. So if you take certain nice covering space, the pullback becomes exact. So therefore you can find some axial function chapter carry A so that its exterior derivative is equal to the pullback of alpha. And then we may try to mimic the Morse theory or Novikov theory to construct kind of same complex. And then if you consider the cohomology or cohomology complex, you would get some cohomology theory, which is now called Floer cohomology theory. So alpha is defined by this formula, and then we do such things. Okay, so now I have to do this. So I don't know, maybe this works. No, this one is not. Okay. So this P is the path space, and so you pick one base path, and then consider another path in the same component. Then you have a family of paths in this space P. So therefore, you can get a map from the square, I mean 0, 1 times 0, 1, to this manifold M. Sorry, this is M. So that this lower boundary is mapped to L0 and the upper boundary is mapped to L1. And then if you define some function on this space by this formula, namely you just integrate omega over this image, then you get some number. You compute the exterior derivative in a formal way, and then actually you come up with this form alpha. So therefore, this A is a locally primitive function of one form alpha. So which somehow, which implies that alpha is really a closed form in formal sense. And now, if you consider the critical point of this function, namely the point gamma, so that dA gamma at xc is equal to 0 for any xc, then this part is arbitrary and omega is non-degenerate. So therefore, gamma dot must be equal to 0. That means gamma must be a constant. So critical point of this is nothing but a constant path. So therefore, you have a critical point as a constant path from L0 to L1. Then you have constant path at the intersection point. Okay? So therefore, the critical point is corresponding to this intersection point. Okay, so now I have to do this again. So I don't know, maybe this one out. Okay. Then you have an intersection point, and then in Morse theory, you have to assume that the function is Morse. I mean, all the critical points are non-degenerate. That condition corresponds to the transversality of these two manifolds. And then you want to compute, you want to define boundary operator by counting the number of isolated gradient trajectories. So in this case, actually, we interpret gradient trajectories of this function A as Z from fixed streets, with boundary on L0 and L1. So then you just understand this, the gradient trajectory in this way, then you try to perform all these constructions. And actually, Andreas Floer realized this idea in the case that these two Lagrangians are Hamiltonian isotopic, and the relative second homotopy group vanishes. And it was Yonggen-Oh who actually extended the theory to a wider situation. And here are some technical conditions like a monotonicity and a minimum absolute number and so on. But anyway, so he actually extended theory up to these things. And he also noticed that this minimal Maslow number condition can be weakened if these two Lagrangians are Hamiltonian isotopic. And this observation is very important for us. Later I may talk about the potential function of Lagrange theory, and that is somehow very, very closely related to these things. Okay, so this is the last thing. So you have a function A, and then you assume Morse condition, and then you interpret gradient trajectory in a proper way, and then study the solution of Holm's curve equations, and then you can cook up certain complex if you are in a good case, and then you can define boundary operator so that boundary operator square is equal to 0, so you can get some cohomology group. But in general, this delta square may not be 0. And trouble comes from the bubbling off of holomorphic disks. So then we are forced to study all homomorphic disks in a systematic way to understand what obstructs the construction. And then we are led to construction of the filter infinite algebra and the bimodules and so on. And using this terminology, we can formulate the obstruction theory or deformation theory of Lagrangian Floer theory. Okay. So here is another sense. Okay. In the Morse theory, yeah, you just consider critical point and gradient flow lines, joining them. And then this is just a easy picture. So you just consider one-dimensional moduli space of gradient trajectories. Then you have only the non-compactness phenomenon by splitting trajectories into bunch of trajectories. Right? Lagrangian Floer theory case, certainly such a thing may happen, right? This or this, but maybe different kind of thing, like a holomorphic disk bubble can also appear. So you may just look at this case. So you have a line and disk, and then consider the holomorphic strip starting from this point back to this point. Then they are parameterized by this segment, length of segment. And if this segment get into this diameter, and then you have this splitting phenomena. But if this one just shrink to a point, and then you just have a holomorphic disk, and then this blue dot is just a constant map. So the gradient trajectory just degenerate to a constant map, and then this one is actually this holomorphic disk bubbles. So therefore, even in such an easy case, you have such a thing. So you cannot really, you have to take care of this. Okay. So from now on, I talk about my joint work with Kaya and Ono. So maybe, I cannot speak so much, but anyway, we use some coefficient ring, so-called Novikov ring. And this one is a kind of formal power series, formal Laurent power series, but the exponent can be any real numbers, but exponent should diverge to infinity, plus infinity. And then actually this one has variation, additive variation, namely you consider the lowest order exponent with non-vanishing coefficient. Then this is the positive part of additive variation, and this is actually variation ring. And the maximal ideal is lambda plus. Okay, so this is our Novikov rings. And then we define so-called infinity operation, namely, we have, so here I consider a case of Durand cohomology. So Durand complex, we cook up certain operations over Durand complex. So actually, it is not so easy to explain this. So I just give you something like this. So actually we consider the modular space of holomorphic disks. And then I put k plus 1 many map points on the boundary, z0, z1 to zk. So you have such a modular space, and then you have bunch of evaluation maps. Then because it's a boundary map point, so it is mapped to L. Right? So if you have k many differential forms, then you can put them back by evaluation map at z1 to zk to get some differential on the modular space. And then you want to integrate along, you make push out this differential form by this evaluation map at z0. And then you get some operation on the Durand complex of L. And if you look at the modular space, a boundary of modular space, actually you have such kind of degeneration. So it may split into holomorphic disks. And from here, we can get certain quadratic relation. And this is the filtered infinity relation. Okay. And then which one? This one. So if this m1 square is equal to 0, then we can take its cohomology. And this is the bottommost type Floer cohomology of L with itself. But as I told you, in general, it is not the case. So we want to deform this M1 so that M1, the deformed M1 satisfies deformed M1 square is equal to 0. So here I list two ways to deform this operator. One is just this. So one is that, so you use some B. B is a actually closed form. Element in the drum complex of L, and then you plug in these B's, arbitrary many number of B's among C1 to Ck, and then sum them up. Then you get some new operator, and this MKB satisfies again filtered infinity relations. And we can also use the ambient cycle, cycle in the ambient manifold M, to deform these MK operators. It is really in a similar spirit as in the big quantum product. So you have a family of quantum product parameterized by the cohomology of the manifold, right? So we can do the same thing. So after using this B and B, you may get this MKB. If M0BB equal to 0, and then we have this, namely this one becomes really a boundary operator. Then we can define Floer cohomology. So the problem now is how to find such a thing, or how to understand this. Right? But we can also weaken this condition. So if this M0BB is not 0, but a multiple of the unit of the drum complex, drum algebra of Lagrangian manifold, we can also show that this M1BB square is equal to 0. And this is a point which is closely related to Yonggen-Oh's observation, which I mentioned before. Even though the minimal Maslov number is equal to, if two Lagrangian Hamilton isotropic, we can define Floer cohomology. So in this case, I consider L with L itself. So therefore, it's Hamiltonian certainly. And then we consider such set of B's by this MC weak B. And then because then this element here, small b, M0BB is a multiple of unit. So therefore, M0BB is a multiple of unit. So we define potential function on this space by this coefficient. So this is definition of potential function. Okay, so I omit this. Okay, so now I come to the toric case. Okay. So as a simplex manifold, now I consider this compact toric Keller manifold. So M is a complex manifold, J is a complex structure over there, and omega is a Keller form. And so that the torus of the same dimension of M acts on it effectively. And then we can define so-called momentum map and denote by P the image of the momentum map. So, for instance, if you have a sphere inside of R3, and then you consider the height function, and this is very easy, the simplest example of this momentum map. If you have CP2 and with standard P2 action, and then you have a triangle in the image of this momentum map. So anyway, so if you have such a polytope, it turns out to be a polytope, convex polytope, P, and pick a point in the interior of this polytope, and then consider inverse image of this point U. So you have a polytope, which is the image of this, and then take an interior point, and then consider it inverse. And then it is a Lagrangian torus fiber over this point U. And it is actually a torus orbit. And in this case, Yeah, actually, so in the previous slide, I defined this MC weak BL, that is we call weak Morrow-Cartan set or weak Morrow-Cartan scheme. And this one actually contains all first cohomology group LU lambda 0. Maybe this statement is strange because I should write something more here. Okay, so in the previous slide, yes, I consider the round complex and then cook up this filtered infinity algebra over this round complex. But in the toric case, everything is actually torus equivariant. The moduli, because J is invariant under T torus action, so therefore the torus naturally acts on the moduli space of holomorphic disks and its compactifications, and then the evaluation maps are equivariant, and we use such property to define filtered infinity algebra over the Tn invariant differential forms. So starting from Tn invariant differential form, and then put them back to the moduli space and push out, and then you get Tn invariant form. So therefore we can define our algebra, filtered infinity algebra on the Tn invariant forms. But such a thing is actually same as the cohomology groups on torus. And then in that sense, actually this one is actually gives us the weak Morrow-Cartan element. So then we define potential function on this set. So therefore, if you restrict it to this, then you have some function. And we can compute the leading order part of this function based on the work by Kelsen Cho and Yonggen Oh. And it has the same form as the Lagrangian superpotential studied in physics. And okay, so but in this case, so we have potential function of the Lagrangian torus fiber. But we can also define some function, which doesn't depend on terms of U, the point in the polytope. We can define some potential function on the so that this thing and these things are simply related by certain coordinate range. So now I consider this potential function. And then we consider some function. If it is polynomial or Laurent polynomial, we have so-called Jacobian ring. Namely, you have a Laurent polynomial ring, and then modeled by ideal generated by the derivative of the function. Right? So this is Jacobian ring. And in the toric Fano case, it was already shown by Bachelet and Giventhal that quantum cohomology is isomorphic to the Jacobian ring of some function. And that function is, in fact, in that case, actually same as this PO of X. Okay? But in general, I mean non-Fano case, our potential function is not necessarily a Laurent polynomial. So therefore, in order to define this Jacobian ring, we have to consider certain completion of the Laurent polynomial ring. And so this is rather complicated, little bit complicated, so therefore I omit it. But anyway, we can define Jacobian ring after this. And then our theorem, based on joint work with Floer, O and Water. So we have a isomorphism between quantum cohomology deformed by ambient cycle B with the Jacobian ring of the potential function deformed by ambient cycle B. And then, this is also actually this is actually the idea how to get this isomorphism in the ring form. So So maybe but I shouldn't do this now. So okay. So anyway, so I have this Jacobian ring, right? And then consider the homomorphism as lambda algebra from this Jacobian ring to lambda. Because this is the kind of algebra, the kind of coordinate ring of the critical point of the potential function. So therefore, we set it as set of critical point of potential function. Yeah, namely, if you have some homomorphism here, and then you just plug in the coordinate variable, and then you get critical point. But anyway, so if you have some homomorphism, you get some critical point, and this critical point is a point in the product of n copies of lambda minus 0. So lambda, and so if you take because it is in lambda minus 0, if you take variation, you take a real number. So now I consider variation. Then the variation of this critical point is a point in Rn. But we can, because of the definition of this, I didn't say this, so we can see that this all the critical points lies over the interior of the momentum polytope. So sorry that I cannot tell you so much about this. So then for critical point, I can take its variation to get a point in the polytope. Okay. Then here is also a theorem. So if we have a critical point, then you can find some Lagrange torus fiber and these B things, so that it has non-vanishing Floer theory, and vice versa. So this way we can find some non-displaced Lagrange torus fiber under Hamiltonian deformations. Okay. So here are some examples. Maybe if I have time, I come back to this. So I have isomorphism as ring, but in fact we have more. So here, if you forget about product structure, it is just a ordinary cohomology with lambda coefficient. And so you have a so-called Poincare pairing here. And over here, we can also define some pairing over it, what we call something like residue pairing. And then this ring homomorphism actually respects these two pairings. So here I have product, quantum product, and Poincare pairing. And then you have actually extended to so-called Florence manifolds, Glaston quantum cohomology. On this side, we have product structure certainly, and then we have this residue pairing, and then we may expect some other Florence structure there. In fact, in the case of polynomial with isolated critical points, then there are such theories. First developed by Kyoto Saito, and later maybe the school by Sabar. So they have some class of polynomials. For some class of polynomials, they can cook up Frobenius manifold structure. So in our case, actually we are working over Novikov ring, so therefore we cannot really apply their theory here, and so their theory is not so general. So at this moment, I cannot say that these two Frobenius structures coincide, because we don't know where about this side. But we expect this actually is isomorphism as Frobenius manifold. And we actually asked Kyoto Saito to develop such a theory, and he's interested in it, so maybe sometime later, maybe we may get something. So finally, I just want to mention the relation with work by Enthoff and Polterdix. So as in maybe the first slide, I showed how the Floer theory is good for, and I mentioned work by Enthoff Polterdix, that is using spectral invariant, they cook up Calabi quasimorphisms and simplex partial quasi-states. So they developed such a theory associated with idempotent quantum cohomology. And using this, their theory, they obtained certain non-dispersible results. In particular, in the case of toric manifold, they can show that there must exist non-dispersed torus fibers. So, and they also introduced some notion like heaviness or superheaviness, and super heavy set must intersect with heavy things and so on. So, and this notion is invariant and Hamilton isotropies. So therefore, they can get criterion for non-dispersibility in these terms. So we have some something. Right? We have something like this. Here we have quantum cohomology here, and then, as I told you, for the critical point, yeah, we have non-vanishing thing Floer theory. Therefore, we have some non-vanishing things. Right? So if I have idempotent this side, then I have idempotent this side, and this idempotent corresponds to certain critical points. Yeah, I have no time to explain this. But anyway, so here I have some idempotent this side. That is corresponding critical point. Then this critical point gives us non-dispersal torus fiber. So there must be some relations. Okay. So what we can observe is the following. So if we have some Lagrangian manifold equipped with certain class P, with bar class B, so that, and then we have this thing. Yeah. So we have a homomorphism from quantum cohomology of the ambient manifold to this Lagrangian Floer theory, and it may be trivial, but the next theorem says the following. Pick an idempotent E here, and then send it by this homomorphism. If it is non-zero, then this Lagrangian manifold must be heavy with respect to the symplectic, partial simplex quasi-state associated with idempotent which we started with. So this is a relation between the, so how to relate their theory with our theory. And in the toric case, actually we can show the following. So let mj omega be compact toric scalar manifold as before, and if this y is the critical point of the potential function, and then this y corresponds to idempotent of the quantum cohomology of the ambient manifold X, so that I denote by this Ey. Right? And then for this y, I take a variation, that is this Uy, which belongs to the interior of the polytope. And so I consider inverse image of this point, then I get some Lagrangian torus fiber. The conclusion is that this Lagrangian torus fiber is super heavy in the terminology with respect to the partial simplex quasi-state corresponding to this critical point. And right. So I think this is, So in this way, somehow we can relate our theory with endospecific theory, and we have a little bit more more applications, like generation of scalar category, which is now joint work with Mohammed Abzaid and Kaya and O and Ota. But I have no time to say about this, so I stop here. Thank you very much for your